Hey everybody, I'm going to take you through the 3.02 practice Nearpod, those answers. Here's your first slide. What's the work done by the dog, friction, gravity, and the ground? So the very first thing we always do is we take a look at the free body diagram. We circle the forces that are parallel to the displacement. So here's our displacement of 3 and the forces that are parallel. So this is horizontal motion, so our horizontal forces are parallel, which means that the other two, the vertical ones, gravity and ground, they don't do any work. So that makes these calculations easier. The reason we do this is because our formula is work equals force parallel to displacement, force parallel D. So if we're looking at the work done by the dog, that would give us, the force is 300 and it's pointing to the right, so that's positive. And the displacement is up here and it's also pointing to the right, so that's also positive. So 300 times 3 gives me 900 joules. This is work of the dog. Okay. Work of friction equal to the force of friction times D. We already circled force of friction. It's pointing to the left, so that's going to be a negative 200. And then times displacement, which again is 3, so that's negative 600 joules. And then for the last two, which is gravity and the ground, I already told you guys, those are vertical, so they don't count, so that's going to be 0 joules. Or they don't do any work. The next part asks about, I can't remember if it asks you to calculate kinetic energy or the speed. I think it's just kinetic energy. So we have E1 plus W equals E2. And the problem tells us that the dog starts at rest. Okay, so right here, the dog's at rest, and then over here, we're trying to find the kinetic energy. And there's only kinetic energy this whole time because this box is on the ground, so there's no GPE, so it's all kinetic energy. So if it starts at rest, there's actually no kinetic energy there at all, so there's 0 energy. The work is the work done by, again, just those two. So work done by the dog plus the work done by friction, which we calculated in the last slide, is equal to kinetic energy 2. Okay, so 0 energy here because at rest on the ground, so no GPE, no KE. Only kinetic energy at point 2 because still on the ground but moving. W dog was 900, W friction was 600. So kinetic energy 2 is going to be 900 minus 600, which is 300 joules. Okay, next one. Starting from rest, Rose pulls a 25 kilogram box across the ground with an angled force. The force diagram shows us the forces. Determine the work done by each force and how fast will it be going after Rose drags it 3 meters. So again, I'm going to start with what are my parallel forces to the displacement. The displacement again is horizontal. So I'm going to circle my horizontal forces. So force of friction, but then the other horizontal force is this 80. And that's part of Rose's angled force. That's the horizontal part. So those are the two. The 80 is pointing to the left, so we're going to call that negative 80, and that's for force of the pull, which is the force of Rose. And then force of friction is pointing to the right, so that's positive. Our displacement is pointing to the left, so this is a negative 3. So I'll find W pull, which is also known as W Rose. That's going to be that negative 80 times negative 3. That's going to be 240 joules. Then we'll do W friction, which should always be negative, so we'll see. The force of friction is 30. And the displacement is negative 3, so yep, we get a negative 90 joules. And then the work of the ground and work of gravity is 0 because those are vertical forces. Okay, how fast will the box be going after Rose drags it 3 meters? So let's do that on the next slide. I don't know why I'm writing that, whatever. So here's what we actually know though, starting from rest. So we know that Rose starts from rest, which means that she doesn't have any energy. So we'll need that. E1 plus W equals E2. She doesn't have any energy at the start. The work is the work of the pull plus the work of friction. And the energy at point 2 is just kinetic. So the work of the pull, let's just double check my numbers here, was 240. Work of friction was negative 90. So we'll do 240 minus 90 gives us kinetic energy 2. And that gives us 150 joules is kinetic energy 2. Okay, we need to solve for speed because it asks us how fast will the box be going. So we know this is kinetic energy. We know the formula for kinetic energy is 1/2 mv squared. And we know the kinetic energy is 150. And I'm pretty sure the mass is 25. Okay. So in this case, let's see, we would do, 300 divided by 25, which is 12, is equal to v squared, which means that v is the square root of 12, which is, oh shoot, 3.46 meters per second. So that's how you answer that one. Okay, here we go. There's Finn. He's pushing a 20 kilogram box. After he pushes it for 3 meters, it moves at 4 meters per second. So it initially starts at 2 meters per second. So that means he has KE here. And then it's moving at 4 meters per second later on. So there's KE at both spots. So we have to determine the following. D equals 3. So KE1, let's go. So KE1 is equal to 1/2 mv1 squared. v1 is 2 meters per second. So 1/2 times 20 times 2 squared. Half of 20 is 10. 2 squared is 4. That means there's 40 joules for KE1. This is part A. All right, I'm going to go over to my free body diagram to determine some stuff about work of the floor, work of fin, blah, blah, blah. So we know that we've got some horizontal motion again. It's pointing directly to the right. So only forces pointing directly to the right and directly to the left are going to do work. So we've got force of friction equals question mark. We're going to figure that out in part F. And then we've got this other force that's 120. That's the force of fin. Okay, so that'll come into play for work of fin. Force of the floor doesn't count, and force of gravity doesn't count in terms of any of the resistance 90. None of those forces do work because they are pointing vertically. They're straight up and down. So that's why they don't do work, because we've got horizontal motion. So for part B, work of the floor, that's 0. Floor is a vertical force. Work of fin, that's going to be the force of fin times displacement, and that's going to give me 120. So it's the force of fin parallel, the parallel part of fin's force. So that's going to be 120 times 3, and that's 360 joules. Wow. What is that, Julie? Okay. Then part D. KE2. So that's 1/2 mv2 squared, which is 1/2 times 20 times 4 squared. Half of 20 is 10. 4 squared is 16. So that's 160 joules. And we're going to have to go on to the next slide for both of these. So they're going to ask us about the work of friction. And here's how we're going to, before I move on, here's how we're going to figure that out. We're going to use that whole E1 plus W equals E2. And we know that W is just going to be the work of friction plus the work of fin. We already know the work of fin is 360. So this is E1 up here. This down here is E2. So we're going to say 40 plus 360, which is the work of fin, plus work of friction is equal to 160. Okay, so here we go. E1 plus W equals E2. So again, that was 40. Right, here's the 40 from KE1 plus W fin, which was, W friction plus W fin. And we calculated W fin down here to be 360. Is equal to E2. And when we go back here, KE2 was 160. So we've got 400 plus work of friction. This is part E, by the way. Is equal to 160, which means work of friction is equal to a negative 240 joules. Okay, and it's got to be negative. Friction never helped anybody, or it never adds energy. Last one, force of friction. So we know that work of friction is equal to the force of friction times displacement. If I go back, I can see the force of friction is circled. That means that it does work. Our displacement is 3. And we just calculated work of friction to be negative 240. So negative 240 is force of friction times 3. We divide by 3 and we get that force of friction is negative 80 newtons, which makes sense. Look, this negative sign means that it should point to the left or down. And when I go back to the free body diagram, it is pointing to the left. So that worked out for us. Okay, next one. Starting from rest, 2 and Tone are pulling a 120 kilogram box along the flat ground as shown. After moving the box for 20 meters, the box moves at 2 meters per second. Determine the following. So here we go. Work of 2. So this, we're going to call this displacement positive 20 meters. The work of 2 is going to be, this is part A, force of 2 times D. And these are both parallel to our displacement. So it's going to be a negative 100 because it's pointing to the left times 20. So that's a negative 2,000 joules. That's part A. Part B, work of Tone is equal to his force, which is 300, times displacement of 20, and that gives us 6,000 joules. Okay, C is work of friction, D is force of friction. So again, we're going to go with E1 plus W, this is part C, equals E2. Again, this starts from rest, so 0. The work is going to be the work of 2, the work of Tone, and then the work of friction. So I'll put W friction here. Then we'll go with work of 2, which was negative 2,000, plus work of Tone, which is 6,000, equal to KE2. KE2 we can calculate because it's moving at 2 meters per second, and the box is 120 kilograms. So 1/2 times 120 times 2 squared. So over here, we've got 4,000 plus work of friction is equal to, let's see, we've got half of 120 is 60. 2 squared is 4. So we've got 60 times 4, which is 240, which means that the work of friction is going to be equal to negative 3760. I'm pretty sure that's right, but only pretty sure. Yeah, that seems right. Okay, then the last one is work of friction. Force of friction. We know that the box moves 20 meters, so I'm going to go to the next one. Work of friction equals force of friction times displacement. Our work of friction, this was the negative 3760 that I was only pretty sure of, times displacement, which is positive 20. So that would mean force of friction is going to be a negative, let's calculate this, shall we? All right, 188 newtons. And that makes sense because it's negative, which means it points to the left. And I had said that the box is moving to the right. So the force of friction should be opposite the motion. Last one. Samantha is pulling this box with an angled force. Friction opposes with a 40 force. If the box starts from rest, how fast will it be going if she drags it across the ground for 5 meters? So our displacement is 5 meters. Okay, so again, it's going to be, we need to do the parallel forces. So force of friction is parallel, and the parallel part of Sam's force is this 120. So that's what I'm going to use. And so we don't, basically what we need to start with is E1 plus W equals E2. Okay, we know the box starts from rest, so 0. The work we have is by Sam and friction. So work of friction plus work of Sam. And that would be equal to KE2. So work of friction is going to be equal to negative 40 times 5. So that's force of friction times displacement. Plus the work of Sam is 120 times 5. Force of Sam, displacement. That's equal to 1/2 times m, which is 10, times v squared. Okay, I'm going to move this up here. So we'll have negative 200 plus 600 equals 5v squared. This would be 400 equals 5v squared, which would give us 80 equals v squared. So v is going to equal the square root of 80, which is going to be 8 point something, almost 9. 80 square rooted. So 8.94. V is 8.94 meters per second. Is that it? That is it.